Welcome to our quiet journey. Tonight we're going to slowly explore those deep questions, the ones that science, even with all its brilliance, still hasn't quite figured out. For all the incredible things we've uncovered, the universe remains absolutely full of riddles, strange situations, and silent wonders that no one can completely explain. Some of these mysteries stretch across the vastness of space, encompassing distant galaxies and the strange pull of black holes. Others are right here on our planet, nestled in the deepest parts of our oceans, swirling through the air around us, and even hidden deep within our own bodies. These unanswered puzzles gently remind us that scientific understanding isn't a book of settled facts, but rather an ongoing story, a narrative that's still being thoughtfully written day after day. Each one of these profound secrets, each quiet unknown, offers a kind of gateway to pure wonder, a soft reminder that we are all just curious explorers within a cosmos far grander than our current comprehension allows. As we drift through these fascinating scientific enigmas, let these questions simply carry you along. If you're ready, we'll begin our exploration now. We truly haven't grasped why anything is here in the first place. This is perhaps the most fundamental puzzle our minds can even conceive, yet it remains completely unsolved. It feels like the most basic thing we could ever ask: why is there something, anything at all, instead of just absolutely nothing? And yet, when we turn to science, there's no clear answer waiting for us. Physics can expertly map out how the cosmos behaves once it's already in motion. Cosmology can meticulously trace the unfolding of events, going all the way back to that incredibly dense, hot moment we call the Big Bang. But the deeper question, about why a universe exists at all, why there are these specific rules that allow it to come into being and persist, that part remains entirely a mystery. Delving into quantum physics, we find that what we perceive as absolute emptiness, the void itself, is actually far from inert. It's brimming with activity, a constant, fleeting dance of particles that shimmer into existence for just an instant, before gracefully disappearing again. Some physicists have put forward the compelling idea that the entire universe itself might have emerged in a similar fashion, suggesting that a state of absolute nothingness is inherently unstable, and that something must always spring forth. Other thinkers propose that perhaps our universe is just one tiny speck within an unimaginably vast collection, a grand multiverse, where each cosmic bubble appears with its own unique set of physical laws. But if that astounding notion turns out to be true, then our initial question simply gets pushed back to an even deeper level. Why, then, should the multiverse itself be there? Why should that exist? Philosophers sometimes suggest that existence is simply the fundamental state of things, that non-existence is an actual impossibility. They might argue that reality, in some form or another, has always been and always will be. But these are deep, abstract ideas that we simply cannot put to the test. No powerful telescope, no sophisticated particle collider can ever truly measure the reason why there is being rather than just nothingness. Every other scientific inquiry, every other question we might pose, rests upon this single, profound foundation. Every distant star twinkling in the night sky, every single atom that makes up your own body, every universal law of nature we observe, all of it exists upon an underlying basis that we simply cannot explain. The sheer fact that reality itself is present at all remains the very deepest mystery we currently face. It's a silent, cosmic wonder, the initial flash that propelled the cosmos into motion, that very first spark, still remains a profound mystery. We have been able to trace the expansive story of the universe back nearly 14 billion years to an epoch when it existed as an incredibly hot, unimaginably dense cosmic fireball. We've given this profound beginning a name, the Big Bang. But the actual event that caused this incredible beginning, that set everything into motion, remains completely unknown to us. Cosmologists have meticulously pieced together a remarkably detailed history of the universe, starting from the very earliest fractions of a second after its birth. In that incredibly brief, initial moment, a staggeringly rapid expansion, a phenomenon known as inflation, might have stretched space itself wide open, inflating it exponentially. But what, precisely, triggered this inflation to begin? Why did it start at all, and then, why did it abruptly come to an end? These fundamental questions are still without clear answers. Some theories about the Big Bang suggest it was a quantum fluctuation, a tiny ripple in the very fabric of reality, a tremor that then gave rise to space and time themselves. Other ideas propose that the Big Bang wasn't a singular, first event, but rather just one chapter in an endless cosmic cycle of births and deaths, with universes continuously expanding, then collapsing, and then beginning anew. What makes this question even more complex is the nature of time itself. If the universe's beginning actually included the birth of time, then asking what existed before that moment might not even make any sense at all within our current understanding. Our most advanced instruments, like the venerable Hubble Space Telescope, the Planck satellite, and the groundbreaking new James Webb Space Telescope, provide us with astonishing glimpses, like snapshots of the universe in its infancy. But none of these incredible tools can truly peer into that first, ultimate instant itself. We understand that the universe had a start, we can precisely measure its age, carefully chart its growth and evolution, and deeply study its faint afterglow. But that initial spark, the true, original cause that set the entire cosmos into motion, is a mystery still completely hidden, veiled in the deepest dark. Time consistently flows forward, yet no one can truly explain why this happens. In every single moment, the present softly slips away, becoming the past. We naturally recall yesterday, but we have no memory of tomorrow. A shattered glass, once broken, never spontaneously reassembles itself. Warmth from a hot cup of coffee always diffuses into the surrounding air, but never the other way around. Time, in our constant human experience, flows in one direction only. We refer to this pervasive phenomenon as the arrow of time. What makes this so peculiar is that the fundamental principles of physics, the very laws that govern the smallest scales of reality, don't actually demand this one-way flow. At those tiny, subatomic levels, individual particles can move both forward and backward through time with equal mathematical consistency. The equations that describe their behavior are perfectly symmetrical. Nothing within those equations insists that time should only progress in a single direction. And yet, our entire existence, our entire perceived world, depends utterly on this undeniable one-way street. Scientists frequently link the arrow of time to the concept of entropy, which is the natural tendency for disorder, or randomness, to steadily increase within a closed system. The universe, it appears, began in an exceptionally ordered, low-entropy state, and it has been gradually running down, becoming more disordered ever since. But why did it begin in such a unique, highly organized condition? Why should the cosmos have started in a state of such low entropy that time could even possess a distinct direction at all? Some physicists speculate that the arrow of time might somehow emerge from the way information spreads and becomes irreversible. Others suggest it's intrinsically tied to the ongoing expansion of the universe itself. Yet, none of these explanations feel entirely complete. Time's unwavering direction is something we are immersed in every single second of our lives. And yet, the profound reason why it flows only forward, never reversing, remains one of the most haunting and deeply personal mysteries in all of science. The vast majority of the universe is composed of something we simply cannot perceive. When astronomers meticulously observe how distant galaxies rotate, they consistently notice something incredibly strange. Stars positioned near the outer edges of these spiral galaxies move far too quickly, as if they are held in place by some unseen, enormous force. Logically, based on the visible matter, those rapidly moving stars should simply be flung away, drifting off into the cold expanse of intergalactic space. Instead, they remain firmly bound within their galaxies. This leads to an unavoidable conclusion: most of the mass contained within the universe is entirely invisible to us. We have named this elusive substance dark matter. Dark matter neither emits light nor absorbs it. Our powerful telescopes, no matter how advanced, cannot observe it directly. Yet, we are certain it must be present because its powerful gravitational influence actively shapes everything around it. It is what holds entire galaxies together, subtly bends the paths of starlight originating from incredibly distant galaxy clusters, and leaves faint, telltale ripples in the intricate structure of the cosmic web. So, the fundamental question persists: what exactly is this mysterious dark matter? Scientists have been searching for decades, pouring immense effort into this puzzle. Some researchers believe it might be made up of undiscovered, exotic particles, perhaps something known as WIMPs, or weakly interacting massive particles. Others suggest it could be axions, which are theoretical, ghostly particles that interact barely at all with the ordinary matter we know. There are even theories proposing that dark matter could consist of black holes that formed in the very earliest moments after the Big Bang. Despite all this enormous effort and ingenious experimentation, we still have no definitive answer. Experiments buried deep underground patiently wait for a single, elusive dark matter particle to collide with an atom, hoping to register a minuscule interaction. So far, none have. For now, this hidden mass, which is 5 times more abundant than all the ordinary matter we can see, remains one of the universe's grandest and most stubbornly unsolved mysteries. An unseen energy is actively pulling space itself apart, making it stretch faster and faster. Back in the 1990s, astronomers were carefully studying distant supernovae, those incredible exploding stars, and they fully expected to observe the universe's expansion gradually slowing down. After all, the collective gravity of all the galaxies should logically be pulling everything back together, or at least decelerating its outward rush. Instead, they made an absolutely astounding discovery: the exact opposite was happening. The universe wasn't just expanding, it was accelerating its expansion. This profound revelation means that some unknown, pervasive energy is embedded within space itself, actively pushing galaxies away from each other at ever-increasing, bewildering speeds. We call this mysterious force dark energy, though that name is really just a placeholder, a label for our immense lack of understanding. Dark energy accounts for nearly 70% of the entire cosmos, yet we still have no idea what its true nature is. One prominent idea is that it's an intrinsic property of the vacuum of space, a kind of constant, inherent energy that's always present even in seemingly empty regions. Another intriguing possibility is that it points to entirely new physics, perhaps a dynamic field that subtly changes over vast cosmic timescales. Some theories even suggest that dark energy could be a sign that our fundamental comprehension of gravity itself is incomplete, requiring a significant overhaul. What makes this mystery even more unsettling are its profound consequences. The ultimate destiny of the entire universe hinges upon this invisible, pervasive force. If dark energy maintains its current, constant strength, galaxies will continue to drift farther and farther apart until, eventually, only cold, empty space remains between them, a fate known as the Big Freeze or heat death. If it were to somehow grow stronger over time, it could, in a terrifying scenario called the Big Rip, eventually tear apart galaxies, then individual stars, planets, and perhaps even atoms themselves. We can precisely measure its effects, but we cannot directly glimpse its true nature. Dark energy is the unseen hand, silently shaping the ultimate, distant future of the entire universe. The fundamental laws of physics seem perfectly calibrated for life, in ways that we still don't fully comprehend. The universe appears to be balanced on an incredibly delicate knife's edge. Imagine if gravity were even slightly stronger, stars, those colossal cosmic engines, would collapse inward far too quickly, never reaching a stable phase for life to emerge. If it were even marginally weaker, galaxies might never have had the chance to properly form, scattering matter too thinly across the vastness. If the electromagnetic force, which governs how atoms bind, were different by just a tiny fraction, atoms might not hold together at all, making complex chemistry impossible. Even the most minuscule alterations in the fundamental constants of physics could completely erase the very possibility of life anywhere in the cosmos. This profound puzzle is widely known as the fine-tuning problem. Why should the intrinsic laws of nature possess the exact, precise values that they do? There's no immediately obvious reason for gravity, electromagnetism, or the nuclear forces to have the specific strengths we observe. And yet, if they were even slightly different, our entire universe would be utterly lifeless. Some observers argue that this is simply an astonishing coincidence, an incredibly lucky roll of the cosmic dice. Others suggest that perhaps countless universes exist, each one governed by its own unique set of laws, and we simply happen to reside in the exceptionally rare one where life is actually possible, a monumental cosmic lottery win. Another deeply intriguing idea is that there might be some deeper, as yet undiscovered principle that fundamentally forces these laws to adopt their exact, specific values. For now, we simply cannot say for certain. But when we gaze out at the countless stars, the planets, and the astonishing fact that we are even here, capable of asking such questions, we are profoundly reminded that the universe feels improbably, uncannily suited for the existence of life. And why that intricate suitability is the case remains one of science's greatest, most humbling mysteries. No one knows if the universe stretches on forever or eventually comes to an end somewhere. The part of the universe that we can actually observe, our observable universe, is incredibly vast, spanning roughly 90 billion light-years from one edge to the other. But we are fundamentally unable to see beyond this immense boundary. Light has only had a finite amount of time to travel since the Big Bang, and so there exists a cosmic horizon, a limit that we cannot peer past. But what, we might wonder, actually lies beyond that distant edge? One compelling possibility is that the universe is truly infinite, stretching out endlessly in every conceivable direction, possessing no boundaries whatsoever. If this is true, then space might contain an unending number of galaxies, stars, and perhaps even an infinite array of other Earth-like worlds, repeating forever. Another fascinating possibility is that the universe is finite but simultaneously unbounded, much like the surface of a sphere. In such a universe, if you could theoretically travel far enough in one consistent direction, you might eventually find yourself returning to your original starting point, having traversed the entire cosmos. Scientists actively search for answers to these questions by studying the cosmic microwave background, which is the faint, ancient afterglow left over from the Big Bang. The subtle patterns within this background radiation might hold crucial clues about the universe's overall shape. So far, the evidence strongly suggests that the universe is very nearly flat, but this finding alone doesn't definitively settle the question of whether it is truly infinite or not. For now, we simply don't know if the cosmos stretches without any discernible end, or if it gracefully loops back on itself in some grand, unimaginable curve. The true size and precise shape of the universe remain deeply hidden, just beyond our current reach, tantalizingly out of sight. beyond the horizon of what we can directly observe, there may be an endless expanse of unknown territories. When we peer into the depths of space, we are also inherently looking back through time. The most distant galaxies our telescopes can detect are sending us light that has journeyed for over 13 billion years to reach us. But beyond that incredible distance lies a region that will forever remain hidden from our view, the unobservable universe. This cosmic horizon isn't like a solid, physical wall. Instead, it's a fundamental limit imposed by the finite age of the universe combined with the fixed speed of light. Beyond this boundary, reality undoubtedly continues, stretching out further into the unknown. But we can never precisely know what exists there, nor how it truly appears. Perhaps it's much the same as our observable patch: countless galaxies, stars, and planets extending far beyond our current sight. Or perhaps it's radically different, with regions governed by entirely different physical conditions, or even fundamentally distinct physical laws. Some theories about cosmic inflation, that incredibly rapid expansion thought to have occurred immediately after the Big Bang, suggest that our observable patch of reality is merely one tiny bubble within a much larger cosmic expanse. If this turns out to be true, then the vast majority of the universe lies forever beyond anything we can ever measure or perceive. We are effectively bound within a cosmic island, our view limited to a small, finite section. The sky filled with stars and galaxies that we see is only the smallest fraction of what may actually exist out there. The rest of the universe, an unimaginable expanse, is truly out there, silent and forever unreachable, a permanent unknown that we can only ponder. Some scientists strongly believe that other universes exist, yet we lack the means to definitively prove this. The concept of the multiverse is one of the boldest and most mind-bending ideas in contemporary science. It proposes that our universe might not be a singular entity, but rather just one among an infinite or near infinite number of others. Each of these hypothetical universes could possess entirely different laws of physics, unique histories, and perhaps even varying numbers of spatial dimensions. This profound concept emerges quite naturally from certain theoretical frameworks. For instance, inflationary cosmology suggests that the process of inflation could spontaneously generate countless bubble universes, each budding off with its own distinct initial conditions. String theory, another ambitious framework, predicts an incredibly vast landscape of possible realities. In such scenarios, our universe would simply be one specific outcome among an immense multitude. This grand idea could even offer an explanation for the fine-tuning problem we discussed earlier. We inhabit a universe perfectly suited for life precisely because only in such universes could conscious observers like ourselves ever come into being. However, there's a significant problem with the multiverse hypothesis. If other universes truly exist beyond our cosmic horizon, we may never be able to directly observe them. No light, no signal, no form of information could ever traverse the boundary between our universe and another. This inherent untestability makes the multiverse concept both incredibly fascinating and highly controversial within the scientific community. It pushes the very definition of what constitutes science, because an idea that we cannot empirically test may never progress beyond pure speculation. Still, the profound possibility that reality is far grander than just our single universe, perhaps infinitely larger, remains one of the most intriguing and deeply philosophical mysteries in modern physics. It's a question that stretches our imagination to its absolute limits. Space and time, those fundamental components of our reality, may actually be woven from deeper rules that we haven't yet uncovered. Einstein's revolutionary theory of general relativity beautifully illustrates that space and time are not merely static, unchanging backdrops against which cosmic events unfold. Instead, they are dynamic, flexible entities. They possess the astonishing ability to bend, to curve, and to stretch, actively shaping the gravitational paths of planets and stars, and influencing the very flow of light itself. But what, at the most fundamental level, is this intricate fabric truly made of? At the incredibly tiny microscopic scales, the two pillars of modern physics, general relativity and quantum mechanics, fundamentally clash. Space and time appear perfectly smooth and continuous in relativity. However, quantum theory suggests that everything should be grainy, fluctuating, and inherently uncertain at those minuscule dimensions. Reconciling these two incredibly successful but conflicting views is one of the greatest and most persistent challenges confronting science today. Some profound ideas propose that space and time are not fundamental at all, meaning they aren't the ultimate building blocks of reality. Instead, they may emerge from something far deeper, perhaps from a complex network of quantum information or from intricate entanglement patterns that collectively give rise to what we perceive as geometry. In this radical picture, what we call space-time is akin to a surface, and beneath that surface lies a more basic, underlying reality that we cannot yet directly observe. Other thinkers wonder if time itself is even truly real, or if it is merely an illusion, a powerful construct created by deeper, more fundamental processes. If this were the case, our most basic, intuitive understanding of reality would be fundamentally flawed. Space and time feel like the grand stage upon which the entire universe unfolds its drama. Yet, the stage itself may not be what it appears to be. What they genuinely are, in their deepest essence, remains one of the most profound, unanswered questions in all of science. A puzzle that touches the very core of our existence. A single particle can somehow exist in two places simultaneously, and we simply don't know how this is possible. Quantum mechanics, that strange and wonderful realm of the very small, informs us that particles don't possess a definite, fixed position until we actually perform a measurement on them. Instead, they exist in what's called a superposition, a kind of probabilistic cloud where multiple potential outcomes are all present at once. An electron, for instance, can literally be both here and there, simultaneously passing through both slits of an experimental setup, interfering with itself almost like a wave. It is only when we actively observe or measure the particle that it seems to choose a single, definite location. This isn't just some abstract theory. Experiments have repeatedly demonstrated superposition in action, not only with tiny electrons, but even with molecules thousands of times larger. Physicists can even meticulously create incredibly delicate states where macroscopic objects seem to exist in these overlapping possibilities. And yet, despite all these observations, no one truly understands what this truly implies. Does the particle physically occupy two distinct locations at the same time? Or is superposition merely a reflection of our incomplete knowledge about its true underlying state? Some interpretations of quantum mechanics suggest that multiple realities split off, one where the particle lands in one spot, and another where it lands in a different place. Others propose that reality itself remains fuzzy and indeterminate until the act of measurement forces it into a definite state. Whatever the ultimate explanation, the astonishing ability of a single particle to seemingly occupy two positions at once remains one of the strangest, most unsettling, and deeply counterintuitive mysteries of modern science. It challenges our fundamental notions of how the world works. Entangled particles seem to instantly echo each other across vast distances, defying our current explanations. When two particles become entangled, their intrinsic properties become linked in a way that utterly defies the concept of distance. If you measure a property of one entangled particle, you instantly know the corresponding state of the other, no matter how far apart they might be separated. Albert Einstein famously referred to this phenomenon as spooky action at a distance. Because it appeared to violate the cosmic speed limit, the idea that nothing should travel faster than light. Yet, countless experiments have unequivocally confirmed that entanglement is a very real aspect of our universe. Photons, electrons, and even small groups of atoms have been successfully entangled and then separated by kilometers. No discernible signal seems to pass between them, yet their correlations remain perfectly synchronized. It's as though nature itself maintains a hidden ledger, ensuring that the outcomes of these paired particles always stay in perfect sync. What does this truly mean for our understanding of reality? Some physicists suggest that reality is fundamentally non-local, implying that the universe is woven together in a much deeper, more interconnected way than our ordinary concepts of space and time allow us to imagine. Others believe that entanglement might point to undiscovered, hidden variables that we simply haven't detected yet, underlying the apparent randomness. Still others propose that information itself, rather than matter or energy, may be the most fundamental foundation of reality. We actively utilize entanglement in emerging technologies like quantum computing and secure communication, yet we cannot definitively explain why it works in such a bizarre fashion. The universe seems to whisper secrets across immense distances, and we still haven't deciphered the mechanism behind these silent communications. It's a profound puzzle, stretching our understanding of causality and connection. No one knows why simply observing something appears to fundamentally change what it is. One of the most bewildering discoveries in physics is the fact that the very act of measurement directly influences the system being measured. In the iconic double-slit experiment, particles behave like waves when no one is actively looking, creating a distinct interference pattern on the screen, as if they're spreading out. But if we decide to measure ager, which slit a particle passes through, its wave-like behavior abruptly vanishes. The outcome changes dramatically, simply because we observed it. Why should this be the case? One leading explanation is that the wave function, the mathematical description of all possible states a particle can be in, collapses into a single, definite outcome only when it is observed. But what, exactly, qualifies as an observer? Is it a mere measuring device, a human consciousness? Or is this collapse just an illusion, perhaps hiding deeper laws that we don't yet perceive? Some interpretations of quantum mechanics suggest that every possibility actually occurs, with reality continuously branching into multiple parallel universes, each representing a different outcome. Others propose that particles only appear definite when information about them becomes irreversible and propagates into the environment. None of these fascinating ideas have been definitively proven. What we do know for certain is that the boundary between the observer and the observed is far less clear-cut than we once believed. The universe, at its most fundamental level, seems to care whether it's being watched, and no one truly knows why this profound interaction occurs. It's a deeply unsettling thought, challenging our intuitive sense of objective reality. Gravity is significantly weaker than every other fundamental force, and we don't understand why this immense disparity exists. Gravity, of course, is the force that governs the entire cosmos. It holds planets in their orbits around stars, shapes the majestic structures of galaxies, and dictates the motion of virtually everything we observe in the universe. And yet, when compared to the other fundamental forces of nature, it is unbelievably, almost comically weak. Consider this: a small, everyday magnet stuck to your refrigerator can easily overcome the entire gravitational pull of the colossal Earth itself. Why is there such an enormous difference in strength? The electromagnetic force, the strong nuclear force, and the weak nuclear force all operate at tiny scales but with immense power. Gravity, in stark contrast, is feeble by comparison. Physicists have been attempting to explain this hierarchy problem for decades without full success. One intriguing possibility is that gravity might somehow leak or spread into hidden extra dimensions that we cannot currently perceive, thereby diluting its apparent strength in our familiar three dimensions. Another idea is that the true, intrinsic strength of gravity is actually quite powerful, but it is somehow masked by unknown physics operating at extremely small distances. Despite centuries of dedicated study, we still don't fully grasp why gravity is so dramatically weaker than the other forces. This fundamental imbalance isn't just a mere curiosity. It's absolutely crucial to the very structure and existence of the universe as we know it. Without this precise weakness, stars and galaxies could not possibly exist in their current forms. The astonishing feebleness of gravity is a quiet mystery, one that paradoxically makes the grand, intricate cosmos possible in the first place. Einstein's general relativity, which describes the universe on a grand scale, and quantum mechanics, which explains the microscopic world, both work incredibly well on their own, yet they stubbornly refuse to fit together seamlessly. General relativity meticulously describes the large-scale universe with an unmatched precision, painting a picture of spacetime as a flexible fabric. Quantum mechanics, on the other hand, illuminates the microscopic world of particles with astonishing accuracy, revealing a realm of probabilities and uncertainties. Each of these groundbreaking theories has been rigorously tested to extreme limits, and both pass every experiment we can devise with flying colors. However, they are fundamentally incompatible with each other. When we try to describe situations where both strong gravity and quantum effects are at play, such as inside the incredibly dense core of a black hole or in the very first moments of the universe's existence, their equations break down completely. Infinities pile upon infinities, rendering the calculations meaningless. The two theoretical frameworks are mathematically irreconcilable. Physicists have spent decades tirelessly searching for a theory of everything that could elegantly unite these two pillars of modern physics. Promising candidates like string theory and loop quantum gravity have offered tantalizing possibilities, suggesting new ways to think about space, time, and matter. However, no experiment has yet been able to definitively confirm any of these unifying theories. Without such a unified framework, we cannot truly understand the universe's ultimate birth, nor the fundamental nature of spacetime at its very smallest scales. The profound fact that our two most successful scientific theories describe seemingly different realities, each perfectly valid within its own domain, is one of the greatest paradoxes in modern science. Both work flawlessly in isolation, yet when we attempt to combine them, they utterly fail. This fundamental disconnect remains a deep and persistent puzzle. The true core of a black hole remains unknowable to us. Black holes are those incredibly dense regions of spacetime where gravity is so overwhelmingly powerful that nothing, not even light itself, can escape its grasp. As matter spirals inward, it is relentlessly crushed toward the very center. According to Einstein's equations of general relativity, everything collapses into a single point of infinite density, a theoretical entity known as a singularity. However, the appearance of infinity in scientific equations is usually a strong indicator that our mathematical models have reached their limits or that our current understanding is incomplete. What genuinely lies at the absolute heart of a black hole? Some researchers believe the singularity is a real physical entity, a place where the known laws of physics simply cease to apply. Others are convinced that a deeper, more complete theory, perhaps one that incorporates quantum gravity, will eventually replace the concept of a singularity with something else entirely, perhaps a tiny, exotic loop of spacetime, a finite, incredibly dense core, or an entirely new kind of object that we cannot currently conceive of or observe from the outside. The event horizon, that boundary of no return, completely shrouds the black hole's interior from any possible observation. For now, the true heart of a black hole remains sealed away, beyond our direct observation and beyond any certain understanding. It stands as one of the most inaccessible and profound mysteries in all of science. We still don't truly understand what singularities genuinely are. A singularity is a theoretical point or region where our equations predict infinite values, density without any conceivable limit, curvature beyond any bound, and time and space themselves collapsing into something utterly beyond definition. Black holes are thought to contain these singularities at their centers. The Big Bang itself may have originated from a singularity. But what are these entities in reality? Are singularities actual physical features of nature, or are they simply stark indicators that our current theories are incomplete, signaling the limits of our present understanding? Many physicists are convinced that they point directly to the limitations of Einstein's theory of general relativity. They believe that somewhere beyond our current models, a new, more encompassing theory, one that successfully merges relativity with quantum mechanics, must take over. In that hypothetical new theory, the troublesome infinities might gracefully dissolve into something finite, understandable, and physically describable. Until such a theory is developed, singularities remain stubborn puzzles at the very edge of our physics. They are places where our current understanding abruptly stops, and our mathematical models completely break down. What lies beyond them is hidden, patiently waiting for a deeper, more complete theory of reality to be discovered. Whether information truly vanishes inside a black hole is still an unresolved question. When matter falls into a black hole, it seems to disappear from our universe forever. However, in the fundamental principles of physics, information, in physics, isn't just about facts or data. It's about the complete quantum state of every single particle, every tiny detail that makes up a system. The core principle in quantum mechanics states that this information must always be preserved, never truly destroyed. But when stuff falls into a black hole, it seems to vanish forever. This creates a huge problem, a deep conflict between two of our most successful scientific theories. General relativity, which explains gravity, suggests that anything crossing the event horizon is gone for good, taking its information with it. Quantum mechanics, however, insists that information can't just disappear. So, what actually happens to all that intricate information once it's swallowed by a black hole? Stephen Hawking, the famous physicist, proposed that black holes aren't completely black. He suggested they slowly leak radiation, a process now known as Hawking radiation. If black holes eventually evaporate completely through this radiation, as his theories suggest, then where does the original information go? If it's truly destroyed, it would break the fundamental rules of quantum mechanics. If it somehow escapes, then that information must be encoded within the Hawking radiation itself, in a way we don't fully understand yet. This perplexing puzzle, known as the black hole information paradox, has stumped physicists for decades. It's one of the most intense debates in modern physics. Some scientists believe the information isn't lost, but is instead somehow encoded on the event horizon itself, that boundary of no return, like a cosmic hologram. This idea links to the holographic principle, suggesting that all the information about a 3D volume can be contained on a 2D surface. Others argue that perhaps black holes don't just lead to a singularity, but might actually connect to different regions of space-time, allowing the information to escape into another part of the cosmos. Still, other researchers think that our very understanding of quantum mechanics might need a significant update or revision to account for this paradox. The fate of information inside a black hole isn't just an abstract problem. It touches on the absolute deepest foundations of reality and how the universe fundamentally works. It forces us to reconsider what information truly means and whether it can ever be truly lost. This question pushes the boundaries of our knowledge, showing us that even our most robust theories have limits and unforeseen challenges. It's a mystery that makes us question the very fabric of existence. Hawking radiation, though famously predicted, has never actually been seen directly. In the 1970s, Stephen Hawking presented an astonishing idea. Black holes aren't truly black in the absolute sense. He theorized that quantum effects happening right near the event horizon should cause them to emit a very faint glow, a kind of radiation. This radiation would mean that black holes slowly, incredibly slowly, lose mass over unbelievably long timescales. Eventually, given enough cosmic time, they could completely evaporate, vanishing into nothingness. This theoretical emission, now named Hawking radiation in his honor, is one of the most celebrated predictions in all of modern physics. It beautifully marries concepts from quantum mechanics and general relativity. However, despite its theoretical elegance and widespread acceptance, we have never been able to observe Hawking radiation directly. The problem is that actual black holes in space are typically surrounded by incredibly hot gas and exist in extremely violent environments. The faint, subtle trickle of Hawking radiation would be completely overwhelmed by all that intense activity and other radiation. Detecting it directly with our current technology, or even technology far in the future, might simply be impossible. Even so, the implications of this idea are immense. It helps bridge the gap between quantum theory, general relativity, and thermodynamics, the study of heat and energy. It suggests that black holes actually possess a temperature, and that spacetime itself is far more dynamic and complex than we might have initially realized. Researchers have tried to create analogs of Hawking radiation in laboratories, using things like sound waves in fluids to simulate the conditions. But these are only indirect hints, not direct observations of the real thing. Whether Hawking radiation truly exists remains unproven. If it does, it will profoundly reshape our understanding of black holes and the universe's most extreme environments. If it doesn't, then something even stranger, something we can't yet imagine, must be happening at the very edge of space-time. This invisible radiation holds a secret to how the universe really works. Black holes might even be secret doorways to other realms, but we just don't know for sure. Black holes are places where the laws of physics are pushed to their absolute breaking point. Inside them, the very fabric of space and time bends and warps in ways that we cannot fully describe with our current theories. Interestingly, some theoretical solutions to Einstein's equations of general relativity proposed that black holes could potentially connect to other distant regions of spacetime, forming theoretical tunnels known as wormholes. In theory, if you could somehow enter a black hole and survive, it might not just crush you to a singularity, but could lead you to an entirely different location, or even a different universe. However, this is purely speculative. Even if wormholes exist in a mathematical sense, they are likely incredibly unstable. The immense, crushing gravity of a black hole would probably destroy anything attempting to pass through it, long before it reached the throat of a wormhole. The journey would be instant death, not a cosmic shortcut. Yet the mathematics themselves do leave this bizarre possibility open. Some physicists even suggest that the singularity at the heart of a black hole could act as a bridge, perhaps to a brand new universe with its own unique laws of space and time. Others hypothesize that black holes might function as cosmic recycling centers, absorbing information and matter from one region and then somehow seeding the birth of new cosmic areas. For now, we can't test any of these wild ideas. no signal or information can escape from a black hole's interior, so its deepest secrets remain completely hidden from us. Still, the thought that black holes could be more than just cosmic graves, that they might be gateways to something truly beyond our universe, is one of the most tantalizing and imaginative mysteries of all. It's a concept that stirs the imagination about what might truly lie beyond the veil of the known. We still haven't figured out how the very first stars were born. When the universe was incredibly young, right after the Big Bang, it was a surprisingly dark and simple place. There were no grand galaxies, no planets circling suns, no heavy metals or complex chemistry. Only vast, diffuse clouds of the lightest elements, hydrogen and helium, gently drifted through the rapidly expanding cosmos. At some critical point in that early cosmic history, those pristine clouds began to collapse under their own gravity, eventually forming the very first stars. This monumental event effectively ended the cosmic dark ages and illuminated the universe for the first time, filling it with light. But exactly how this profound transformation happened, how those first stars ignited, remains a deep mystery. These pioneering stars, often referred to as population Aetheri stars, are thought to have been truly enormous, perhaps hundreds of times more massive than our own sun. They would have burned incredibly hot and bright, but also lived incredibly short, furious lives, lasting only a few million years before dramatically exploding as immensely powerful supernovae. These first stellar explosions were crucial. They seeded the early cosmos with the very first heavier elements, those essential building blocks forged in their fiery cores. This chemical enrichment then paved the way for the formation of subsequent generations of stars, and eventually for planets and all the complex chemistry required for life. The big problem is that we have never actually seen one of these population Aetheri stars. They lived and died so quickly and so incredibly long ago that direct observational evidence is missing. Astronomers are constantly searching for indirect clues, looking for subtle chemical fingerprints in the oldest surviving stars, hoping to find hints of those violent first births. The powerful new James Webb Space Telescope might finally glimpse their light or their chemical traces. But for now, the exact process that triggered the very first stars to shine remains one of the great unsolved questions in astronomy. It's like a missing chapter in the universe's autobiography. Some galaxies managed to form supermassive black holes far too quickly in cosmic history. At the absolute heart of almost every large galaxy, including our own Milky Way, lies a supermassive black hole. These colossal objects are millions, sometimes even billions, of times more massive than our Sun. We have a good understanding of how black holes can grow over time. They slowly accumulate gas by swallowing gas, dust, individual stars, and even merging with other black holes. But in the very early universe, we observe evidence of black holes that grew to be absolutely enormous, reaching supermassive proportions far too rapidly. Some of these colossal giants already existed less than 1 billion years after the Big Bang. According to our current models of black hole growth, there simply wasn't enough time for them to have accumulated so much mass through ordinary processes. This presents us with a significant puzzle. Did these early giants form from the direct collapse of incredibly massive primordial gas clouds, essentially skipping the smaller, intermediate steps of star formation and stellar, mass black holes entirely? Or did they perhaps grow from the explosive deaths of the very first generation of massive stars, collapsing into black holes that were much larger than we typically expect? Or is there some entirely new mechanism that we haven't yet discovered, one that allowed them to feed and expand at astonishing, unprecedented rates? These ancient, rapidly grown black holes challenge our fundamental understanding of how galaxies evolve and how these central behemoths come to be. If we can solve their mystery, we might unlock critical insights into the entire story of how galaxies themselves first formed and developed. For now, they remain cosmic enigmas, these impossibly large giants that, by all accounts, should not have existed so soon after the universe began its grand journey. No one knows why so many galaxies naturally take on those elegant spiral shapes. When we think about galaxies, our minds often picture those beautiful, graceful spirals with sweeping arms of stars gently curling outward, like immense cosmic pinwheels. Our own home galaxy, the Milky Way, is a perfect example of this stunning phenomenon. But why, exactly, should galaxies form such intricate and aesthetically pleasing spiral patterns in the first place? The answer isn't entirely clear. One popular idea suggests that these spiral arms are actually density waves, similar to how traffic jams form on a highway. Stars don't permanently reside in the arms. Instead, they move through these denser regions, bunching up as they pass, which creates the Buller's illusion of stable, permanent arms. Another theory proposes that spiral patterns might be shaped by gravitational interactions, with galaxies gently tugging on each other, stirring their vast populations of stars into these distinctive, curving arms. Computer simulations can successfully recreate spiral structures, but they don't always do so with perfect consistency or explain every observed detail. Spiral galaxies are far from rare. In fact, they're quite common across the cosmos. And yet, their precise origin and the mechanisms that maintain their stability remain largely unsettled. Why some galaxies develop into these breathtaking, beautiful spirals while others simply become featureless, elliptical blobs is still an open question in astrophysics. When we gaze up at the night sky and see the luminous band of the Milky Way stretching across it, we are, in a very real sense, looking from inside one of these profound mysteries. Our home galaxy's elegant arms are both intimately familiar and profoundly unexplained. They're a silent testament to the universe's artistic flair, a puzzle written in starlight. Fast radio bursts, or FRBs, flash across the cosmos, and their precise cause is still a mystery. In 2007, astronomers made an astonishing detection, a powerful, incredibly brief radio signal that lasted for only a few milliseconds. Since that initial discovery, hundreds more of these enigmatic signals have been found, scattered seemingly at random across the vast expanse of the sky. These intense, fleeting signals are now known as fast radio bursts, or FRBs. Each one of these bursts releases an incredible amount of energy, as much as our sun produces in an entire year, but compressed into the mere blink of an eye. What could possibly be causing such immensely powerful, yet incredibly short, cosmic flashes? Some FRBs have been observed to repeat, meaning they burst multiple times from the same location. This suggests they might originate from ongoing processes, such as magnetars, which are incredibly magnetic neutron stars that can flare with astonishing bursts of energy. Other FRBs appear only once, hinting at catastrophic, singular events, such as the complete collapse of a massive star, or the violent merger of two incredibly dense, compact objects like neutron stars or black holes. However, no single explanation seems to fit all the observed characteristics of these diverse FRBs. These powerful bursts travel across billions of light years of intergalactic space, often becoming distorted and stretched by the diffuse matter between galaxies. Scientists are even hoping that FRBs might eventually help us map the distribution of matter across the entire universe. But until we can definitively pinpoint their exact sources, they will remain intriguing cosmic puzzles. Every so often, the universe sends us a brief, incredibly powerful shout across the void. We can hear it, we can measure its properties, but we still don't know who or what is actually speaking. Pulsars glow with a perfect, almost unsettling regularity, and their incredible precision still puzzles us. Pulsars are the collapsed, incredibly dense remnants of massive stars, specifically neutron stars. These exotic objects spin at astonishing rates, sweeping powerful beams of radiation across space, much like cosmic lighthouses. When they were first discovered back in 1967, their signals were so incredibly regular that scientists initially wondered if they might be artificial signals from intelligent extraterrestrial life. Today, we know that pulsars are entirely natural phenomena, but their precision remains absolutely astonishing. Some pulsars keep time better than even our best atomic clocks, rotating hundreds of times per second without missing a single beat. How can such an extreme object, a star that has been crushed into a sphere only the size of a city, maintain such incredible rotational stability over vast periods of time? The answer lies in their extreme density and their incredibly powerful magnetic fields. But the precise details are still not fully understood. Pulsars can also occasionally experience sudden glitches, where their rotation speed abruptly changes in ways that we cannot yet accurately predict. These glitches might originate from complex interactions deep within their superfluid cores, where the physics operates under conditions unlike anything we can create or observe on Earth. Pulsars are essentially natural laboratories for studying extreme physics, but they still hold many secrets. Their precise, rhythmic pulses remain some of the most mysterious and yet astonishingly accurate signals emanating from the universe. They are a constant reminder of the incredible and often baffling phenomena that populate the cosmos. Magnetars erupt with strange, intense bursts of energy, and we don't fully understand why. A magnetar is a very specific type of neutron star, but it possesses a magnetic field that is 1,000 times stronger than that of a typical neutron star and an unimaginable trillion times stronger than Earth's magnetic field. These colossal magnetic fields within a magnetar can become incredibly twisted and stressed, eventually snapping and releasing sudden, incredibly violent bursts of high-energy radiation. A magnetar can unleash more energy in just a single second than our Sun produces over 100,000 years. We detect these eruptions as intense flares of X-rays and gamma rays. But what exactly triggers these cataclysmic events remains deeply uncertain. Are these powerful bursts caused by starquakes, which are sudden shifts in the rigid crust of the neutron star under immense magnetic stress? Or are they caused by rapid reconfigurations of the magnetar's magnetic field itself, releasing stored energy much like a snapping cosmic rubber band? Some fast radio bursts, AFRBs, have even been linked to magnetars, suggesting that these incredibly powerful objects might be responsible for at least some of those mysterious signals we discussed earlier. However, the full picture of magnetar behavior is still very much incomplete. Magnetars are relatively rare, with only a few dozen currently known, but their sheer power is absolutely staggering. They serve as potent reminders that the universe contains engines of energy that we still struggle to fully comprehend or explain. Cosmic rays continuously strike Earth with incredible power, and their ultimate origin is still unknown. Every single second, high-energy particles called cosmic rays bombard Earth from outer space. Most of these particles are protons traveling at speeds incredibly close to the speed of light. Many originate from our own sun or from supernova explosions within our galaxy. However, some of these cosmic rays are so incredibly energetic, so immensely powerful, that we have absolutely no idea where they come from. The most extreme cosmic rays carry as much energy as a fast, pitched baseball, but this energy is packed into a single, subatomic particle. No known astrophysical process should theoretically be able to accelerate particles to such extreme speeds. They might originate from the immediate vicinity of supermassive black holes, from the cores of incredibly active galaxies, or perhaps from some exotic, as yet undiscovered processes that operate in the most extreme corners of the universe. When these ultra-energetic particles smash into Earth's atmosphere, They create spectacular showers of secondary particles that we can detect with ground-based observatories. Facilities like the Pierre Auger Observatory in Argentina meticulously track these events, attempting to trace the paths of these particles back to their cosmic origins. However, powerful magnetic fields scattered throughout space bend their trajectories, effectively scrambling and erasing the clues about their true source. Cosmic rays are constant, invisible visitors from the depths of space. Yet, their most powerful examples remain a profound mystery. They serve as a humbling reminder that somewhere in the vast universe, nature operates particle accelerators that are far more powerful than anything humanity could ever hope to construct. It's a silent, constant bombardment from the unknown. Vast cosmic voids stretch across space, and their formation remains unclear. The universe isn't uniformly filled with matter. Instead, galaxies are arranged in an enormous, intricate cosmic web, forming vast clusters and long, thin filaments of matter. These structures are separated by truly enormous, seemingly empty regions called cosmic voids. Some of these voids span hundreds of millions of light-years, appearing almost completely devoid of galaxies. Why are these colossal empty spaces there? Computer simulations suggest that gravity naturally pulls matter together into the dense filaments and clusters, which then, by necessity, leaves these vast empty spaces behind. This is a natural consequence of cosmic evolution. However, the very largest voids we observe are often bigger than our simulations predict, which raises intriguing questions about how they truly formed. Do they perhaps hint at new physics? Maybe some subtle aspect of how dark energy shapes the large-scale structure of the universe? Or are they simply statistical extremes, rare but naturally possible fluctuations in the cosmic distribution of matter? These voids actually affect how light travels across the universe, subtly distorting the paths of light from distant objects. They might even offer crucial clues about the fundamental nature of dark energy itself. But for now, their true origins and exact formation mechanisms remain uncertain. Looking into a cosmic void is like staring into absolute nothingness on the largest possible scale. They are among the loneliest and most desolate regions in existence, vast expanses of emptiness with no clear, satisfying explanation for their immense size. They represent an emptiness that is itself a profound mystery. How the universe will ultimately end is still a completely unanswered question. The universe definitely had a beginning, but will it also have a definitive end? Scientists are currently considering several possible scenarios for the universe's ultimate fate, each one depending on the precise nature of dark energy and the delicate balance of cosmic forces at play. In one scenario, often called the heat death or big freeze, the universe would continue to expand forever, endlessly cooling down. Eventually, all stars would burn out, all galaxies would slowly fade away, leaving behind only a cold, dark, and incredibly diffuse emptiness, utterly devoid of energy and activity. In another, more dramatic scenario, the expansion of the universe might eventually reverse itself, pulling everything back together into an incredibly dense, hot state, a catastrophic event known as the Big Crunch. This would be a reversal of the Big Bang. A third, even more unsettling possibility is the Big Rip. In this terrifying scenario, dark energy would grow stronger over time, not just expanding space but actively tearing apart structures. It would first rip apart galaxies, then individual stars, then planets, and eventually, even the very atoms themselves, leaving behind only fundamental particles isolated in an expanding void. Which of these fates awaits our universe? We simply don't know yet. Current observations strongly suggest that the expansion will continue indefinitely, perhaps leading to a heat death. However, the exact properties and long-term behavior of dark energy remain too uncertain for us to make a definitive prediction. The universe could potentially last for trillions upon trillions of years, fading slowly, or it might meet a far more sudden and dramatic end. For now, the ultimate future of everything, of stars, of galaxies, and of life itself, remains one of the greatest, most profound unanswered questions in all of science. It's a cosmic cliffhanger. Something incredibly powerful triggered cosmic inflation, but no one knows what it was. In the earliest, infinitesimal fraction of a second, after the Big Bang, the universe is thought to have undergone an unimaginably rapid expansion, far exceeding the speed of light. This process is known as inflation. This theory is very successful at explaining why the cosmos appears so smooth and uniform across vast distances, and why the tiny quantum fluctuations present in the early universe eventually grew into the seeds for the galaxies we observe today. However, the fundamental question remains, what actually caused this incredible inflationary epoch? That part is still a complete mystery. Some theories propose the existence of a hypothetical energy field, often called the inflaton field, that briefly dominated the universe immediately after the Big Bang, before gracefully fading away. This field would have provided the immense energy needed to drive such a rapid expansion. Other ideas suggest that inflation is somehow intimately tied to the quantum structure of spacetime itself, perhaps an inherent instability in the vacuum. We can see the subtle fingerprints of inflation in the cosmic microwave background radiation, where faint patterns and temperature variations remarkably match what the inflation theory predicts. However, the true underlying cause of inflation, and whether it actually happened precisely as described, is still a subject of active debate and intense research. Something made the universe grow unimaginably fast, creating the vast stage for everything that followed. But the specific spark that drove this inflation, the ultimate trigger, is still unknown, representing a hidden, pivotal chapter in the universe's origin story. It's a missing piece in the cosmic puzzle. The origin of life on Earth is still one of the greatest unknowns. Life on our planet began over 3.5 billion years ago, but the intricate details of its very first appearance remain deeply hidden in the mists of time. Fossil evidence clearly shows that microorganisms were already thriving relatively soon after Earth cooled enough to support liquid water. But how, exactly, did non-living chemistry cross that incredible threshold into becoming something alive? How did inert molecules spontaneously organize themselves into the first self-replicating, evolving systems? One prominent idea, known as the RNA world hypothesis, suggests that life initially began with simple RNA molecules, which are capable of both storing genetic information and acting as catalysts, before the more complex DNA took over as the primary information carrier. Another compelling idea is that life emerged from the energy-rich environments found around hydrothermal vents on the deep ocean floor. Here, hot, mineral-rich water pours out from cracks in the Earth's crust, providing a constant source of chemical energy and a complex mix of molecules that could have combined to form life's building blocks. Still others propose that the fundamental building blocks of life may have actually arrived on Earth from outer space, carried here on comets or meteorites that heavily bombarded the young planet. Each of these ideas has some scientific support, but none have been definitively proven. Scientists have successfully managed to create amino acids, the basic components of proteins, and other essential molecules in laboratory conditions designed to mimic the early Earth. However, producing a fully living, self-sustaining system from scratch remains far beyond our current capabilities. The origin of life may have been a unique, incredibly rare event, or it might be a natural outcome whenever the right conditions are present throughout the cosmos. Until we uncover much clearer evidence, the precise moment when chemistry first awakened into biology remains one of science's deepest, most profound mysteries. We don't know if life first began in the depths of the ocean or on ancient land. Our early planet offered a variety of potential cradles for the very first forms of life. The vast, global ocean, covering much of Earth's surface, seems like the most obvious candidate. Within these oceans, hydrothermal vents, where superheated water and minerals stream from the seafloor, provide both rich chemistry and a constant supply of energy. Many scientists strongly believe that life may have originated in these deep sea environments, with complex molecules assembling within natural mineral compartments protected from the harsh surface conditions. However, there is another intriguing possibility that has gained traction. Some researchers argue that shallow pools on land, those exposed to cycles of drying and refilling, could have played a crucial role. These cycles would have concentrated molecules, driving the chemical reactions necessary to form life's fundamental building blocks. Ultraviolet light from the sun, which is often destructive to complex molecules, could also have provided the energy needed to power key steps in these early reactions. Both of these environments, the deep ocean and shallow land pools, appear plausible, each offering its own strengths and facing its own set of challenges. The vastness of the ocean might have diluted crucial molecules, making it harder for them to interact and combine. Conversely, land-based pools might have been too unstable, with extreme fluctuations in temperature and chemistry. Until stronger, more definitive evidence emerges from ancient rocks or new experiments, we simply don't know whether life first stirred in the dark, pressurized depths of the oceans or in the sun-drenched, shallow waters of primeval land. The answer remains hidden in the deep past, in rocks and fossilized traces that have long since been transformed and altered over eons. No one truly knows how the very first living cells were formed. Life, as we understand it, is defined not just by its unique chemistry, but by its incredible organization. Modern cells are astonishingly intricate structures, complete with protective membranes that separate them from the outside world. Inside, countless molecular machines diligently carry out a vast array of reactions, maintaining the cell's functions. But how did this first, complex cell actually arise from a chaotic mix of lifeless chemicals? One fascinating possibility suggests that fatty molecules, which were naturally abundant on the early Earth, could have spontaneously formed tiny, spherical bubbles. These primitive membranes might have trapped useful chemicals inside, creating a localized environment. These early compartments could have allowed energy and molecules to flow in and out, while simultaneously protecting fragile chains of RNA or proteins from the harsher external environment. Over immense periods of time, the chemistry contained within these bubbles could have become progressively more complex, eventually leading to a self-sustaining, self-replicating system. Experiments have shown that simple membranes can indeed form spontaneously under the right conditions, much like oil droplets in water. However, the monumental leap from these basic, primitive compartments to the astonishing complexity and self-sufficiency of a fully living cell remains largely unknown. This transition from disorganized chemistry to the very first organized, self-replicating cellular unit stands as one of the greatest mysteries in all of biology. Until we understand this crucial step, we cannot truly say how life ultimately began. DNA adopted a very specific double helix shape, but why it did so remains a mystery. All known life on Earth, from the smallest bacteria to the largest whales, uses the exact same molecule to store its genetic information, DNA. Its iconic double helix structure is both elegant and universal, carrying the precise instructions for building and operating every single organism. But why this particular molecule, and why this specific, intricate shape? From a purely chemical perspective, there are many possible ways to store information. RNA, for instance, is a simpler molecule and is widely thought to have played a more central role in early life before DNA took over. Yet, at some pivotal point in life's ancient history, DNA became the master code, the universal blueprint. Its remarkable stability, its ability to replicate with astonishing reliability, and its capacity to carry immense amounts of information made it uniquely suited for this role. However, we still don't definitively know why DNA's specific structure, a double helix with precisely paired bases E, adenine with thymine, guanine with cytosine, became the exact solution that all life on Earth now depends on. Was this particular structure an inevitable outcome, dictated by the fundamental laws of chemistry, meaning it was the only viable option? Or was it more of an accident, a single successful evolutionary outcome among countless failed alternatives, a stroke of cosmic luck? The sheer universality of DNA across all life suggests that it might indeed be the most efficient and robust answer nature could find for storing genetic information. Still, the precise reasons why life chose this exact chemical and structural path remain an open question, hinting at deep, underlying mysteries in the fundamental chemistry that underpins all existence. It's a silent enigma woven into our very being. The origins of viruses are still very unclear. Viruses are truly strange entities in the biological world. They are not considered live in the traditional sense, primarily because they cannot reproduce on their own. Instead, they operate as parasitic hijackers, relying entirely on the cellular machinery of living cells to make copies of themselves. Yet, they are far from inert molecules. They actively evolve, adapt to new hosts, and profoundly influence the course of life on Earth, including our own. So, where did these peculiar agents come from? Some scientists propose that viruses are ancient relics of the hypothetical RNA world, surviving remnants from an era before fully living cells with DNA had evolved. This would make them incredibly old, perhaps even predating cellular life. Other researchers believe that viruses originated as pieces of genetic material, such as DNA or RNA, that somehow escaped from cells and then evolved the ability to copy themselves independently, becoming parasites. A third intriguing possibility is that viruses were once full-fledged living organisms that, over eons, gradually became stripped down to their simplest, most essential form, losing many of their cellular components as they adapted to a parasitic lifestyle. The truth may be even more complex. It's possible that viruses arose in more than one way, meaning their origins could be as diverse and varied as life itself. What is clear, however, is that they are incredibly ancient. They may even have played a crucial role in the evolution of complex life forms, acting as agents that transfer genes between different organisms, thereby accelerating genetic diversity. Viruses continue to blur the fundamental line between what we define as life and non-life, and their beginnings remain one of biology's most enduring and fascinating mysteries. They are everywhere, yet we don't know their initial story. Some molecules became alive, while countless others did not, and we don't know why. The early Earth was an incredible chemical playground, a dynamic environment where simple molecules were constantly forming everywhere. This included deep-sea hydrothermal vents, active volcanic pools, and even within lightning-struck atmospheres. Amidst this chemical richness, some molecules began to spontaneously link together, forming more complex chains, such as amino acids, the building blocks of proteins, and nucleotides, the building blocks of DNA and RNA. However, only a tiny, minuscule fraction of this vast chemical diversity ever crossed that incredible, defining line into becoming what we would call life. Why those specific molecules, and not others? What unique properties or conditions allowed some to organize themselves into self-replicating, evolving systems, while the overwhelming majority of chemicals remained inert? Was the emergence of life an inevitable outcome, once the right basic ingredients came together in the right environment? Or was it an incredibly rare accident, a cosmic fluke dependent on a highly improbable sequence of chance events? Experiments designed to mimic early Earth conditions suggest that many of life's basic building blocks can indeed form spontaneously under natural circumstances. However, creating a truly self-sustaining, evolving chemical system that can genuinely be called alive remains elusive in the laboratory. The leap from mere chemistry to genuine biology is vast, almost incomprehensible, and we don't yet understand how it happened. This profound uncertainty raises deep philosophical questions about our place in the cosmos. If life is an inevitable process, then the universe might be absolutely teeming with living worlds. If it was an exceedingly rare fluke, then we, on Earth, might be utterly alone in this vast cosmic ocean. The mystery of why certain molecules transitioned into life while countless others remained inert is one of the most important and fundamental unanswered questions in all of science. It touches on our uniqueness, or lack thereof. We still don't know if life exists anywhere else in the immense universe. Earth is, so far, the only place we have definitively found where life thrives. But when we consider the sheer scale of the cosmos, billions of stars in our own galaxy, and billions of galaxies stretching far beyond, it seems incredibly unlikely that we are truly alone. Yet, despite decades of dedicated searching, employing various methods, no clear, undeniable evidence of extraterrestrial life has ever been found. We've made incredible strides, discovering thousands of exoplanets, many of which orbit within the habitable zone around their stars, where conditions could potentially allow for liquid water to exist on their surfaces. We also know that organic molecules, the chemical building blocks of life, are incredibly common throughout space, found on comets, within vast interstellar clouds, and even on distant moons within our own solar system. Mars, our planetary neighbor, shows compelling geological signs of a much wetter past, with ancient riverbeds and lake basins. Moons like Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, both harbor vast, hidden oceans beneath their icy crusts. The raw ingredients and seemingly favorable conditions for life appear to be abundant across the cosmos. And yet, despite all this promise, the silence persists. We haven't detected any clear, unambiguous signals from intelligent civilizations. We haven't found definitive microbial life on Mars, nor have we uncovered any alien fossils on other worlds. It's entirely possible that life is indeed common, but simply very difficult to detect across such immense distances. Or it could be that life is exceedingly rare, requiring a very specific set of conditions that we don't yet fully understand. Until we discover even the simplest alien microbe, the profound question of whether life exists anywhere else in the universe remains completely unanswered, a silent cosmic enigma. It is the ultimate question of cosmic companionship. Could life form from a chemistry completely different from ours? We simply don't know. All life on Earth, every single organism we've ever studied, is built upon the same fundamental chemical foundation: carbon as its backbone, water as its solvent, and DNA and proteins as its primary information carriers and workhorses. But does it have to be this way? Could life exist elsewhere in the universe with a completely different chemistry, using entirely different elements and molecules? Some scientists seriously consider the possibility of silicon-based life. Silicon is abundant in the universe, and like carbon, it's capable of forming long, complex molecular chains, which are essential for biological structures. Others imagine organisms that might use ammonia instead of water as their primary solvent, or exotic biochemistries thriving in lakes of liquid methane, like those found on Saturn's moon Titan. Still others wonder if even more speculative forms of life could exist, perhaps based on plasma, magnetic fields, or even information itself as a fundamental organizing principle. We don't yet have the answer to these mind-bending questions. All of our current definitions and understandings of life are inherently shaped by the single example we have: Earth life. It may be that carbon and water are indeed the only truly viable chemical solutions for complex, stable life to emerge. Or it could be that the universe holds living systems that are far stranger, more diverse, and more unimaginable than anything we can currently conceive. If we were to discover alien life based on a fundamentally different chemistry, it would likely look nothing like us. Such a discovery would profoundly challenge our very definition of what it means to be alive, forcing us to expand our understanding of biology in ways we can only begin to guess. How common truly habitable worlds are is still incredibly uncertain. Astronomers have made astonishing progress, discovering thousands of planets orbiting other stars, known as exoplanets. Many of these detected worlds are small and rocky, similar in size to Earth, and some even reside within the habitable zone around their parent star, the region where temperatures are just right for liquid water to exist on the surface. But how many of these worlds are truly habitable in a way that could support life as we know it? That crucial detail is still largely unknown. Habitability depends on far more than just a planet's distance from its star. Planets need to possess the right kind of atmosphere to retain heat and provide protection, a strong magnetic field to shield them from harmful stellar radiation, and long-term geological stability. Some exoplanets, even in the habitable zone, might be scorched by intense radiation, while others could be perpetually frozen due to a lack of internal heat or a thick, reflective atmosphere. Even moons, like those orbiting gas giants, could potentially be habitable, harboring vast oceans beneath their icy crusts. However, with our current technology, we cannot yet measure their precise conditions directly. The galaxy might be absolutely teeming with truly habitable worlds, like countless jewels scattered throughout the cosmos. Or they might be incredibly rare, precious diamonds. Right now, we simply cannot say for certain. Each new discovery of an exoplanet brings us closer to an answer. But the true frequency of Earth-like conditions, the exact prevalence of worlds where life could genuinely take root and flourish, remains one of the great open questions in astronomy. It defines our cosmic solitude or crowdedness. We still can't answer the oldest question of all: are we truly alone? For as long as humans have gazed up at the stars, we have pondered this fundamental question of whether life exists beyond Earth. Despite the colossal size of the universe, despite the sheer abundance of planets now being discovered, and despite the widespread presence of the chemical ingredients for life scattered across space, we still have no definitive answer. We actively listen for signals from potential extraterrestrial civilizations using powerful radio telescopes, participating in projects like SETI. We send robotic probes to explore planets and moons within our own solar system, searching for biosignatures. We meticulously analyze the atmospheres of distant exoplanets, looking for chemical signs that might hint at biological activity. But so far, the cosmic silence has been complete. It's entirely possible that simple life, like microbes, is common throughout the universe, but intelligent, technological civilizations are exceedingly rare or perhaps very short-lived. It may be that life, at every level of complexity, is exceptionally rare, making our existence a singular, precious cosmic accident. Or it could be that life is indeed everywhere, but it remains hidden from us, either by immense distances, by fundamental differences in its form, or by methods of communication we don't yet understand. The question remains wide open, a constant source of wonder and speculation. Are we a lonely spark in a vast, empty universe, the only ones capable of conscious thought and questioning? Or are we just one voice in an immense cosmic chorus that we simply haven't heard yet? Until we find undeniable evidence one way or another, the answer to this oldest and most profound of human questions remains unknown. Consciousness clearly arises from the brain, but we don't fully understand how it happens. Every thought you have, every single memory, every fleeting flicker of awareness, all of it seems to emerge from the incredibly complex organ residing within your skull, the brain. Scientists can precisely measure electrical signals moving across the vast networks of neurons. They can even switch awareness off and on using anesthesia. They can track the brain's activity with advanced imaging when you focus on a specific picture or listen to a sound. Yet, none of this incredible scientific insight fully explains why there is an inner, subjective experience at all. Why should firing neurons, mere electrochemical impulses, create the profound feeling of being alive, of I am? A brain scan might show intense activity in your visual cortex when you observe a sunset, but it doesn't explain why that experience is accompanied by the vivid, internal glow of red and gold inside your mind. It can show the circuits that process sound, but it doesn't explain why hearing your favorite song evokes such deep, moving emotions. Researchers have put forward many fascinating ideas. Perhaps consciousness appears when information seamlessly spreads across the entire brain, or when neurons form certain, specific, highly complex patterns of activity. Some even speculate that awareness might be a deeper, more fundamental property of the universe itself, not just an emergent phenomenon of the brain. But none of these ideas truly bridge that colossal leap from mere matter to the subjective, internal world of the mind. Consciousness is, paradoxically, the most ordinary thing imaginable. It's what you are experiencing right now, every second of your existence. And yet, when we try to fully explain it, it constantly slips through our fingers, remaining elusive. We know it originates from the brain, but the how remains the deepest mystery of all. Dreams fill our nights, but their ultimate purpose is still unknown. Every single night, as you gently surrender to sleep, your mind actively conjures entire worlds. Some of these dream worlds are incredibly vivid, populated with people and places you recognize from your waking life. Others are strange, fragmented, and often dissolve almost immediately upon waking. These are dreams. And even though every human being experiences them, no one truly understands why they happen or what their fundamental purpose is. Some scientists believe that dreams are the brain's way of practicing or rehearsing. They might replay recent memories, strengthening useful connections and consolidating learning. Others think dreams help us regulate our emotions, providing a safe, unreal space to process and work through fears, sadness, or conflicts without real-world consequences. Still others argue that dreams are simply random firings of a sleeping brain, disconnected signals that are then patched together into somewhat coherent stories by our minds as we try to make sense of them. What makes dreams even more puzzling is their sheer power and intensity. A terrifying nightmare can jolt you awake in a cold sweat, filled with terror, even though you are perfectly safe in your own bed. Conversely, a pleasant, fulfilling dream can leave you smiling and feeling uplifted throughout the entire day. Sometimes, dreams even offer unexpected solutions to waking problems. Many writers, artists, and scientists have described significant breakthroughs or creative inspirations that came to them during sleep. We know that the brain is highly active while we dream, especially during REM's rapid eye movement sleep, when the eyes rapidly flicker beneath closed lids. But the deeper purpose behind this nightly mental theater remains elusive. Dreams are a familiar part of our lives, these nightly journeys into strange, fantastical lands, yet their true meaning and function are still profoundly hidden. Time feels slower or faster depending on our internal state, and no one knows why. Think for a moment about a time when a critical moment seemed to stretch out, slowing down to an absolute crawl. Perhaps a near accident, a sudden fright, or any intensely emotional experience. Now, consider the opposite, a wonderful vacation that seemed to vanish in an instant, or hours that simply disappeared when you were completely absorbed and lost in something you deeply enjoyed. Our external, clock-based time is perfectly steady and consistent, but our subjective sense of time is anything but. Why is this? No one knows for sure. Some researchers believe the brain possesses an internal clock, and that strong emotions like fear can dramatically speed it up, while states of calm or relaxation can slow it down. Others suggest that our brain judges the passage of time by the number of distinct events it processes. A moment filled with many new details and experiences feels longer, while a routine or uneventful moment feels much shorter. This theory could potentially explain why childhood summers seem to last an eternity, while adult years seem to slip past with increasing speed. Childhood is full of novelty, adulthood often more routine. But these are only theories. What we do know is that time, as perceived by the mind, is incredibly elastic. It stretches, it contracts, and sometimes it even seems to stand completely still. The objective seconds and minutes are constant, but our internal experience of them is a deep mystery, flowing according to rules we don't yet fully understand. We don't yet understand how memories are stored and then recalled. Your entire life story, your first day of school, your happiest moments, your deepest regrets, every single experience is stored somewhere within the intricate network of your brain. And yet, how precisely those memories are preserved, and how they magically return to your conscious awareness, exactly when you need them, is still a profound mystery. Scientists know that memories aren't like neatly organized files in a cabinet. Instead, they are complex patterns of activity spread across countless neurons, distributed across many different brain regions. The hippocampus, a small, seahorse-shaped structure deep in the brain, plays a crucial role, helping to weave these patterns together, acting as a kind of central index or librarian for new memories. But exactly how the brain initially encodes an experience into a lasting memory, and then later retrieves that specific memory from its vast archives, is not fully understood. Sometimes, memories are surprisingly fragile. They can even change slightly when we recall them, being subtly reshaped or re-edited before they are stored away again. We can even, astonishingly, create false memories that feel absolutely real and vivid, even though the events never actually happened. Why do some memories endure for an entire lifetime, remaining crystal clear, while others fade away within days or weeks? Why does a particular smell, a specific sound, or a piece of music suddenly unlock a vivid, long-forgotten scene from childhood? Experiments offer tantalizing glimpses, specific neurons firing when a known face is seen, or patterns of brain activity that mirror the act of memory recall. But the full, comprehensive picture is still missing. Memory is the invisible glue that fundamentally makes us who we are, connecting our past to our present. And yet, the intricate machinery behind it. How moments become an indelible part of our personal history and how they resurface years later is still one of the brain's most enigmatic secrets. Our emotions run incredibly deep, but their ultimate origins remain mysterious. Emotions shape nearly every aspect of human life. Joy propels us forward, fear holds us back, anger flares up, and sadness weighs heavy on our spirits. But where, precisely, do these powerful feelings come from? Scientists understand that emotions involve the body as well as the brain. Your heart races when you're afraid, your stomach might knot with anxiety, and tears well up when you're sad. These physiological responses are undeniable, but the deeper origins of these subjective feelings themselves are still intensely debated. Are emotions hardwired into our biology, ancient survival tools built into our genetic code over millions of years of evolution? Or are they constructed by the brain in real time, shaped by our culture, our personal memories, and our interpretations of events? We know that certain brain regions play significant roles: the amygdala for fear processing, the insula for disgust, and the prefrontal cortex for regulating and modulating emotional responses. However, there isn't a single, isolated emotion center in the brain. The experience is distributed and complex. Music can inexplicably give us goosebumps, a particular scent can trigger sudden, powerful nostalgia, and sometimes, we don't even know why we feel the way we do, only that the feeling is intense and real. Emotions are powerful, often subconscious guides, steering our choices and behaviors frequently more profoundly than pure reason does. Yet, the precise way they arise, the way they take such a profound hold of both body and mind, remains one of the most intimate and deeply personal mysteries of being human. Creativity appears in sudden, brilliant sparks, but we don't know where it actually comes from. Imagine an artist staring at a blank canvas, a writer facing an empty page, or a scientist grappling with an unsolved problem. Hours might pass with seemingly nothing happening, no new ideas forming. And then, suddenly, an idea arrives. Clear, surprising, vibrant, and alive. Where did it come from? Creativity often feels like a spontaneous spark, a flash of insight. But its origin is stubbornly hidden from our direct view. Some researchers suggest that creativity is essentially the brain's ability to mix and match old ideas, concepts, and experiences in novel, unexpected ways, forming new connections. Others believe it often requires stepping away from the problem, allowing the subconscious mind to work in the background while the conscious mind rests or focuses on something else. Indeed, many historical breakthroughs in art, science, and invention have come not at desks or in laboratories, but during dreams, while taking a shower, or during quiet, contemplative walks. Brain scans show that different neural networks are involved in creative processes. Some are active in generating new ideas, while others are involved in judging and refining those ideas. But even this doesn't fully explain that profound moment of inspiration. Why does the solution or the creative concept arrive so suddenly, and often with such a powerful sense of certainty? Why do some people seem to overflow with innovative ideas, while others struggle to produce even a single novel thought? Creativity is undeniably one of humanity's greatest gifts, shaping our art, driving scientific progress, and fueling every major innovation. Yet, the precise place where ideas originate, that quiet, mysterious leap from nothingness to something truly new, is a mystery we still cannot explain. It's a silent miracle within us. Déjà vu makes the present feel strangely repeated, and no one knows why. You step into a room you've never been in before, or you find yourself in a new situation, and suddenly, everything feels strangely, uncannily familiar. You might even feel a fleeting sense that you know what's going to happen next, even though logically you couldn't possibly. This is déjà vu, a common but profoundly unsettling experience, and it remains one of the strangest mysteries of the human mind. Scientists have proposed several explanations. Some suggest it might be a subtle trick of memory, perhaps the brain momentarily misfires, creating a false signal of familiarity without any actual past memory to back it up. Others think it happens when one part of the brain processes and experience a tiny fraction of a second before another part, making the identical moment feel like a repeat. When the second part catches up, still others propose it arises from subtle similarities between a current scene and a forgotten past one, subconsciously fooling the mind into believing it's a direct re-experience. What makes déjà vu so mysterious is its sheer intensity and fleeting nature. For a few seconds, reality feels doubled, simultaneously new and deeply remembered, creating a momentary disconnect. Almost everyone experiences it at some point in their lives, Yet no one can predict when or why it will occur. Déjà vu gently reminds us that memory and perception are far more fragile and complex than we might assume, and that the brain sometimes plays tricks on us in ways we don't yet fully understand. It's a fleeting glimpse into the peculiar workings of our own minds. Placebos can genuinely heal, but the underlying power behind them is still a mystery. Imagine taking a pill, being confidently told by a doctor that it will alleviate your pain, and then actually feeling better, even though the pill contained absolutely no active medication at all. This is the placebo effect, and it is a very real, scientifically documented phenomenon. Doctors have observed placebos effectively reducing pain, easing symptoms of depression, and even calming the tremors associated with Parkinson's disease. The effect is widely believed to stem from expectation and belief. The patient's conviction that something else will help triggers genuine physiological and psychological changes in the brain and body. Placebos can stimulate the release of the body's natural painkillers, known as endorphins, alter brain chemistry, and even subtly affect the immune system. What makes the placebo effect even stranger is that it can sometimes work even when people are explicitly told they are taking a placebo, a pill with no active ingredient. Somehow, the ritual of treatment, the act of taking a pill, the trusted presence of a doctor, the expectation of relief, taps into hidden healing pathways within the human system. But why some people respond so strongly to placebos, experiencing significant relief, while others do not, is still largely unknown. The placebo effect blurs the traditional line between mind and body, powerfully demonstrating that belief and context itself can sometimes initiate healing processes in ways we still don't fully understand. It's a testament to the incredible, untapped power of the human mind over the body. We don't even know why we need sleep at all. Every single night, we willingly surrender to sleep. We close our eyes, drift into the strange worlds of dreams, and lose conscious awareness for many hours. But why do we need it? From an evolutionary perspective, sleep is inherently dangerous. In the wild, an animal that is deeply asleep is incredibly vulnerable to predators. Yet, virtually every species on Earth, from insects to humans, engages in some form of sleep. This universality strongly suggests that sleep is absolutely essential for survival and well-being. But essential for what, precisely? Some scientists believe sleep plays a crucial role in helping the brain consolidate and store memories, as well as facilitating learning processes. Others think it's vital for clearing away metabolic waste products that accumulate in the brain during waking hours, essentially, cleaning the brain. Sleep may also be critical for restoring physical energy, regulating complex emotions, and strengthening the immune system. It might even help the brain prune and rewire its neural connections, maintaining overall balance and efficiency. And yet, no single explanation fully accounts for all the diverse evidence we've gathered. Different animals exhibit remarkably different sleep patterns and needs. Dolphins, for example, sleep with only one half of their brain at a time, allowing them to remain partially aware and continue swimming. Some birds can even sleep while flying during long migrations. And some creatures, like certain insects, seem to need very little sleep at all. What we know for sure is that without adequate sleep, both our minds and bodies quickly begin to break down, leading to severe cognitive and physical impairments. Why we spend roughly 1/3 of our lives in this vulnerable, unconscious state remains one of science's greatest, most fundamental mysteries. We still don't fully understand why aging happens the way it does. Every living being on Earth, without exception, undergoes the process of aging. Skin eventually wrinkles, hair turns gray, muscles weaken, and eventually, the body's complex systems begin to fail. But science cannot yet fully explain why aging happens, nor why it unfolds in such remarkably different ways across the vast spectrum of species. One prominent explanation points to our DNA. Each time a cell divides, the protective caps at the ends of our chromosomes, called telomeres, naturally grow shorter. Eventually, these telomeres become so short that the cell stops dividing altogether, entering a state of senescence or even programmed death. Another theory attributes aging to accumulated damage. Reactive oxygen molecules and other metabolic byproducts slowly but relentlessly corrode cells and tissues over time, leaving behind damage that accumulates throughout life. Still, other scientists view aging as a complex side effect of evolution, a trade-off that allows an organism to focus its energy on reproduction and growth in youth, but leaves the body more vulnerable to decline afterward. Yet, nature presents us with intriguing exceptions to these general rules. Some species of turtles and fish show almost no discernible signs of aging, remaining biologically youthful for centuries. Certain jellyfish, astonishingly, appear able to revert to earlier stages of life, effectively sidestepping the aging process altogether. Naked mole, rats, small rodents live far longer than expected for their size, displaying remarkable resistance to many age-related diseases. Why do some creatures possess such incredible resilience against aging, while humans succumb to it with such predictability? And why does the process unfold with such a consistent, predictable pattern in our own species? The answers to these questions remain elusive. Unlocking this profound mystery could revolutionize medicine forever, offering new ways to combat age-related diseases and extend healthy lifespans. But for now, aging remains a fundamental riddle, written deep into the very cells that make up our bodies. The limits of human lifespan remain uncertain. The longest confirmed human life recorded ended at 122 years. But was this specific age the absolute upper ceiling of human biology, a hard limit beyond which no human can pass? Or was it merely a remarkable outlier, a rare individual who pushed the boundaries of what's statistically probable? The truth is, no one truly knows for sure. Some researchers argue that humans do indeed have a fixed, biological hard limit to their lifespan. They contend that beyond a certain age, the body's intricate repair mechanisms simply cannot keep up with the relentless accumulation of damage, making survival increasingly improbable. Evidence suggests that human survival rates decline sharply after the age of 110, hinting at a biological cap. Others, however, insist that there is no strict maximum lifespan, only ever-increasing odds of frailty, disease, and random chance playing a role in mortality. What's particularly puzzling is that while average life expectancy has climbed dramatically over the last century, thanks to advances in medicine, hygiene, and nutrition, this maximum human lifespan has barely budged. Almost no one lives past 115, regardless of where they live or when they were born. Still, scientists are actively searching for ways to extend healthy human life further. They study families of supercentenarians, who remain remarkably healthy into extreme old age, looking for genetic predispositions. They also investigate genes that confer resistance to disease and rigorously test drugs that have shown promise in slowing aging in animal models. Could humans someday reach 150 years or even 200 years of age? The current data offers tantalizing hints but no certainty. The ultimate upper boundary of human life remains hidden, waiting for someone to discover whether it is a fixed, immutable barrier or a flexible limit that can be pushed much further through scientific understanding. Some animals possess the incredible ability to regrow entire limbs, and we can't explain how. If a salamander loses a leg, astonishingly, it can grow a brand new one, perfectly formed and functional. If a starfish loses an arm, it will slowly but surely rebuild it over time. Even certain worms can regenerate an entire body from just a single small fragment. In the natural world, this remarkable ability to regenerate lost body parts is surprisingly common across diverse species. But humans, with all our biological sophistication, cannot do it, except in the tiniest, most limited ways. A child's fingertip might regrow a small portion, but a lost limb never returns. The fundamental question is, why can they do it, and we cannot? Scientists studying salamanders have found that when these creatures are injured, the cells near the wound seem to reset or dedifferentiate. They roll back into a flexible, embryonic-like state, losing their specialized identities. From there, these versatile cells can then grow into new muscles, bones, and nerves, perfectly organized to form a complete, functional limb. Humans share many of the same fundamental genes as these regenerating animals. Yet, for reasons we don't yet understand, our bodies do not activate or utilize these genes in the same powerful, regenerative way. If we could unlock this incredible biological ability, medicine would be utterly transformed. Damaged hearts could heal themselves, severed spinal cords could regrow, and lost limbs could potentially return. Yet, despite decades of intense study, the full blueprint of regeneration remains deeply hidden from us. Why nature bestowed this miraculous power upon some creatures while denying it to us is a profound mystery. For now, full limb regeneration belongs to the salamander, the starfish, and a select few others. A biological miracle we can only observe with silent awe. Certain creatures live far longer than expected, and we don't know why. Most animals generally follow a predictable pattern. These smaller bodies tend to have shorter lifespans, while larger bodies live longer. A mouse lives for a few years, while an elephant can live for many decades. Humans, with our relatively long lives among primates, are somewhat of an outlier. But scattered across the natural world are creatures that defy these rules entirely, behaving like biological rebels. The Greenland shark, for instance, glides silently beneath the Arctic ice for centuries, its lifespan stretching beyond 400 years, making it the longest living vertebrate. Bowhead whales sing their mournful songs in frozen seas for over 2 centuries. Tiny naked mole rats, despite their small size, live an astonishing 10 times longer than similar rodents, displaying remarkable resistance to many age-related declines and diseases. Some species of clams have even been discovered alive after more than 500 years. Why do these creatures possess such extreme longevity? Scientists have found tantalizing clues. Some have unusual proteins that resist cellular damage. Others possess DNA repair systems that appear to be remarkably efficient at fixing genetic errors. Still others exhibit metabolisms that operate at an incredibly slow, deliberate pace, reducing wear and tear. But no single answer explains all of these diverse examples. Each species seems to hold its own unique key to extreme longevity, and humans have not yet been able to fully copy or understand these secrets. These creatures serve as powerful reminders that aging is not a fixed, immutable law of nature, but rather a complex puzzle with many potential solutions. If we could truly learn their secrets, we might one day unlock new ways to extend our own healthy lives. For now, they remain timeless enigmas of the natural world, silently defying our expectations. Some animals can survive being frozen solid, yet their secrets remain hidden. Imagine being frozen completely solid, your blood crystallized into ice, your heart utterly silent, your body rigid and unmoving. For the vast majority of living creatures, this would mean certain death, but not for all. The wood frog of North America, for example, literally freezes solid during the harsh winter months. Its heart stops beating. Its body becomes stiff and brittle. Yet, when evidence of extraterrestrial life has ever been discovered, we've managed to identify thousands of exoplanets, many of them orbiting within the habitable zone, around their stars, where conditions might allow for liquid water to exist on their surfaces. We also know that organic molecules, the chemical precursors to life, are incredibly common throughout space, found on comets, within vast interstellar clouds, and even on distant moons within our own solar system. Mars, our planetary neighbor, displays compelling geological evidence of a much wetter, warmer past, with ancient riverbeds and lake formations. Moons like Europa and Enceladus, orbiting Jupiter and Saturn respectively, hide vast, salty oceans beneath their icy crusts, oceans that could potentially harbor life. The conditions that seem conducive to life appear to be abundant across the universe. And yet, despite all these promising signs, the silence persists. We haven't detected any definitive signals from intelligent civilizations. We haven't found any undeniable microbial life on Mars. We haven't uncovered alien fossils anywhere. It's possible that life is indeed common, but simply incredibly difficult to detect, perhaps existing in forms or using communication methods we don't yet recognize. Or, conversely, it may be that life is exceedingly rare, requiring a highly specific set of conditions that we don't yet fully understand. Until we find even the simplest alien microbe, the profound question of whether life exists anywhere else in the universe remains completely unanswered, an echoing silence in the cosmic theater. Could life actually form from a chemistry that is totally different from our own? We honestly don't know. All the life we have ever encountered on Earth is built upon the same fundamental chemical foundation: carbon as its backbone, water as its solvent, and DNA and proteins as its primary information carriers and workhorses. But does it absolutely have to be this way? Could life exist with an entirely different chemical makeup? Some scientists ponder whether silicon, which is abundant in the universe and capable of forming long, complex chains, could potentially serve as the structural backbone for alien life forms. Others imagine organisms that might utilize ammonia instead of water as a solvent, or exotic biochemistries thriving in the frigid methane seas found on Saturn's moon Titan. Still others wonder if even more abstract forms, like self-organizing plasma, intricate magnetic fields, or even information itself, could somehow host something akin to life. We currently lack the answers to these speculative questions. All of our current definitions and understandings of life are heavily shaped by a single example: life on Earth. It may very well be that carbon and water are, in fact, the only truly viable chemical solutions for complex life to emerge. Or, it could be that the universe holds living systems that are far stranger and more diverse than our wildest imaginations can currently conjure. If we ever discover alien life, it might look absolutely nothing like us. It could fundamentally challenge our very definition of what it truly means to be alive, forcing us to expand our biological horizons. How common truly habitable worlds are is still incredibly uncertain. Astronomers have made remarkable progress, discovering thousands of planets orbiting stars beyond our Sun. Many of these exoplanets are small and rocky, much like Earth, and some are situated within that crucial habitable zone where liquid water, a key ingredient for life, could potentially exist on their surfaces. But how many of these worlds are genuinely habitable, capable of sustaining life for long periods? That remains a profound unknown. Habitability depends on far more than just a planet's distance from its star. Planets also need the right kind of atmosphere, sufficient magnetic protection from stellar radiation, and long-term geological and climatic stability. Some planets in the habitable zone might be scorched by intense radiation, while others might be frozen solid due to a lack of internal heat or a thick atmosphere. Even moons, like those we discussed, could potentially be habitable, harboring vast oceans beneath their icy crusts, but we cannot yet measure their conditions directly. Our galaxy might be absolutely teeming with habitable worlds, or they could be incredibly rare, precious jewels scattered sparsely across the cosmos. Right now, we simply cannot say for sure. Each new exoplanet discovery brings us closer to an answer, but the true frequency of Earth, like conditions and genuinely life, Sustaining environments remains one of the great open questions in astronomy. We still can't answer the oldest question of all: are we alone? For as long as humanity has gazed up at the stars, we have pondered whether life exists beyond our Earth. Despite the immense, incomprehensible size of the universe, despite the sheer abundance of planets, and despite the widespread distribution of life's basic chemistry across space, we still have no definitive answer. We actively listen for signals from distant civilizations using powerful radio telescopes. We send robotic probes to explore planets and moons within our own solar system. We meticulously analyze the atmospheres of distant exoplanets, searching for any telltale signs or biosignatures of life. But so far, the silence is profound and complete. It may be that simple microbial life is common, but intelligent, technological civilizations are exceedingly rare, or perhaps incredibly short-lived. It may be that life itself is rare at every single level, making us a singular, improbable accident. Or it could be that life is everywhere, but it remains hidden from us by vast distances, or by fundamental differences in its form or communication methods. The question remains wide open. Are we a lonely, solitary spark of awareness in an endlessly vast and empty universe? Or are we just one voice, waiting to be heard, in a grand cosmic chorus that we simply haven't tuned into yet? Until we find undeniable evidence, the answer to this oldest and most profound of human questions remains completely unknown.